The next type of vector multiplication we're going to talk about is cross product, or also sometimes called the vector product. And so as the name indicates, our result from this type of vector multiplication is going to be a vector. And this is going to be the second type of vector multiplication that we're going to commonly use. So let me go ahead and write our equation here. So it's going to be A cross B. So again, we're assuming two generic vectors A and B. And so again, this is read as A cross B is equal to the magnitude of A times the magnitude of B times the sine of theta AB times a unit vector U sub n. And I'm going to define what a couple of these things are in a minute. But we can note that this notation, again, this A cross B, this cross product, is something that we saw in our Maxwell's equation. So hence why we want to investigate it. So again, our theta AB rather, is the smaller angle between A and B. So that's the same as what we saw with our dot product. The smaller of the two angles between A and B. So same basic idea as the dot product. And then our U sub n is a unit normal vector, or let's say it's a unit vector, which is normal to the plane containing A and B. So basically we're going into a third dimension with this unit normal vector. So a unit vector normal to the plane containing our vectors A and B. So if we think about, for instance, A and B both being in the plane of the page, then our unit vector, our unit normal vector, U sub n, is either going to be coming out of the page towards us or into the page sort of away from us. So how do we determine which direction this U sub n is going? So we can use something called the right-hand rule. So direction is determined with our right-hand rule. And so this is another thing that you might be familiar with from physics or some other similar class. So sometimes I'll just abbreviate this RHR, right-hand rule. And so basically what our right-hand rule says, and I'm going to write it out and then we're going to look at it graphically, is first we want to align the fingers on our right hand with our first vector, in this case A. So align fingers of our right hand. Let's see if I can write correctly, with A. And so in this case we're saying A because A is our first vector here. So our second step is then going to be to curl our fingers towards our second vector, in this case B. So curl fingers, and of course these are still the fingers on our right hand, towards B. And so again, this is just our second vector here, in this case B. And then sort of our third item, which is our result, is that our thumb on our right hand is going to be pointing in the direction of U sub n. So thumb points in direction of our unit vector U sub n. So let's sort of draw out an example, and you can kind of run through these steps and see if you can figure out what the direction is. So let's say we have vectors A and B in some plane. So here is our vector B. Here is our vector A. Okay. And so of course, first of all, what we can say is that we have some angle between our two vectors here. This is theta A sub B. Notice that it's the smaller of the two angles as opposed to this larger one here. So that's how we define that theta A sub B. So if we want the direction of our unit normal vector U sub n, we put the fingers on our right hand in line with A, and then we want to be able to curl them towards B, and we note that our thumb is pointing sort of up. And so what we can do is we can draw a direction here. I'm going to put a little square to indicate that that's at a right angle with that vector A and B. And we can say this is our A, the direction for our A cross B. Now to figure out the magnitude, of course, we could do this calculation up here, magnitude of A, magnitude B, sine of theta AB. Another sort of interesting graphical trick is if we want to find the magnitude of that, we can just find the area of this parallelogram. So the magnitude of A cross B is equal to area of the parallelogram. And that's not something that you often use, but sort of just an interesting side note. Okay, so we can also define this a little bit differently. The same way we saw for our dot product, we had two definitions, sort of two different equations. So let's use a similar thing. Let's say if we have A is equal to AX, AY, AZ. So we have an X, Y, and Z component in our A vector. And we define B similarly. We say we have an X component, a Y component, and a Z component for our B vector. Then we can write the cross product as follows. So A cross B is equal to the determinant of, and we're going to have a determinant of a 3 by 3 matrix. Our first row are our unit vectors UX, UY, and UZ. And our second row are our components of our vector A. So AX, AY, and AZ. And then finally, our third row is our components of our vector B, BX, BY, and BZ. And so if you're unclear on how to do detail or how to do a 3 by 3 determinant, let me know, but sort of just writing out our results briefly here, we can say that this ends up being, so it's a little more messy than our dot product, but we have AY times BZ minus AZ times BY, all of that in our X direction. Now we have minus the product of AX BZ minus AZ BX in our Y direction, plus, and then for our last term we have AX times BY minus AY times BX, all of that in our Z direction. And again, we're going to look at an example a little later on to see how we actually do this with numbers, but keep in mind as our calculations get more complicated, we can use software such as MATLAB to make our life a little simpler if needed. So let's look now at some properties of our cross product. Okay, so first of all is that our cross product is not commutative. So not commutative. And so basically what this is saying is that the order that we do our cross product matters. So A cross B is not equal to B cross A. And so if we think about our definition with our right-hand rule and how we applied that, that sort of makes sense. And what we can see is that our cross product is actually something called anti-commutative. And so what that means is basically if we switch the order, we have to put a negative sign in there. So if we have A cross B, that's actually equal to negative B cross A. And again, if we think back to our right-hand rule and how we applied that, that makes sense. So our second item is that it is not associative. So not associative, which basically means, again, our order is mattering. So we can't say that A, well, let me restate that. So A cross the quantity of B cross C is not equal to the quantity of A cross B cross C. So basically the order in which we do cross product matters. So that's what we see from these first two properties. Our third property indicates that our cross product is distributive, however. So it is distributive. And so we can see that if we have a cross product, so A being crossed with the sum of two vectors, so A cross the quantity B plus C, well, that is equal to A cross B plus A cross C. Okay, and then the final one is scaling. So this is related to just multiplying by a scalar. So if we have some scalar value k, multiply that by a and then cross that by b, basically we can move this value k anywhere in this equation. So we can say it's a cross that scalar value times b, or we can say it's that scalar value times the cross product of A and B. So we can kind of move that anywhere. And again, just to write explicitly, K is a scalar value here. One other thing that we can note in terms of our unit vectors, so remember we considered how our unit vectors and our dot products related, is that if we have ux cross uy, that's equal to u of z. If we have u of y cross u of z, that's equal to u of x. And then finally we can say if u of z cross u of x, if we have that, that's equal to u of y. And of course, from our anti-commutative property up here, what we can see is if we switch the order of any of these, we basically just get a negative. So for instance, if we change this to y cross x, we would just have negative z. And so basically, we can consider this below, and what this ultimately means is that in this text, and typically what is done with EMAG in general, is that we're working with right-handed coordinate systems. So right-handed. So there is such a thing as a left-handed coordinate system, but it's not often used. So let me just sketch out really briefly what our sort of axes look like. So of course, if we typically would draw our z here, our y here, and our x here. And so if you go through and you use that right hand rule, you can kind of confirm any of these three things here. So for instance, let's look at this first one. If we put our fingers in the direction of x, curl them towards y, we notice that the thumb on our right hand is pointing in the direction of z. So what I want you to take away from this is that you need to be careful about how you define axes. So be careful about axes definitions. So for example, oftentimes we'll be shifting our axes around, and as we'll talk about in the next unit, we're going to look at different coordinate systems. So we basically want to set it up to make our math as easy as possible. So for instance, what we could do is we could sort of shift, we could maybe call a different one z, a different one x, a different one y to fit a problem better. But for instance, let's say we wanted to call this one x, we wanted to keep this y, and we wanted to keep this as z. Well, it turns out we can't do that because we don't have this right-handed coordinate system anymore. Because for instance, if we look at this first one again, we now have x cross y using our right hand rule. That's telling us that z should be in this direction, but it's not. So basically what that means is that these are incorrect labels. So we just want to be careful that we are defining everything appropriately in sort of line with our right-handed coordinate system.